Good morning and welcome to our webinar on how to use Wagner's CFT Design Guide and what things you should consider during design using FRP that differs from traditional materials. I'm Kelly Stewart, Marketing Manager at Wagners CFT, and I'm here with Principal Structural Engineer Rohan McElroy from icubed Consulting. Rohan has more than 15 years' experience in the industry, working on an array of projects from mining, residential and commercial buildings to industrial developments. And Rohan has a particular interest in designing using fibre reinforced polymer profiles. Before we get started, just a few webinar protocols. We are going to be recording today's event and plan on making the recording available to people who were unable to attend via our YouTube channel. We're going to run through Rohan's presentation first and hold any questions until the end. You'll see at the top of your screen, there's a chat tab where you can submit a question anytime during the webinar, and I will compile those questions for discussion at the end. Also, I'd like to flag at the end of the webinar, I will send you out via email a feedback form. It's really quick to complete, and the information you provide us will help continually improve our webinar series. So, without further ado, I'd like to introduce icubed Consulting Principal Structural Engineer, Rohan McElroy. Well, just hold on there a second, Rohan. It looks like your microphone is off. If you could just turn it on, please.
Sorry, how's that?
Perfect.
Yeah, sorry about that. So thank you, Kelly, for the introduction there. We're going to be discussing the Wagner CFT Design Guide today and a bit of the background behind it and how you can use it for engineering applications for infrastructure projects into the future. So as Kelly sort of outlines, my name's Rohan. I'm from icubed Consulting. We're a civil structural firm based in Brisbane, Queensland. We have an office in Melbourne, an office in Perth as well. Our business is largely set up around infrastructure projects and renewable energy markets. So Wagners and icubed have been working closely together for probably sort of 15 to 20 years. We've worked on a bunch of different projects ranging from boardwalks and bridges to road bridges and wharfs and pontoons around Australia and around the world. For those who don't know, Wagners protrude their own FRP composites in Toowoomba at their factory. And they produce a number of different section sizes. So you can get square hollow sections, circular hollow sections, RHS sections in different sizes, which are all outlined in the design guide. And what we do with those sections is we can combine them, which I'll show you in the next slide, to create stiffer beams and elements to span further and carry additional load. For those who don't know too much about FRP, it has some really great benefits in the infrastructure market, especially in marine environments. It's corrosion resistant. It's 100% non-ferrous solution, so there's no iron in any of the material makeup of the cross-section or the connections. It's durable, termite resistant, it's lightweight. There are some applications where we'll actually use composites over steel because of its lightweight nature. And for those who are sort of working on carbon footprint projects, it has a low embodied energy. And I'd recommend you have a read through the section in the design guide about the embodied energy for the composite material itself. So really briefly, the protrusion process, I won't go into too much detail here. This is a pretty specific item that the CFT guys can explain a bit further in some of the presentations they've done. But in the composite section itself is made up of glass rovings and a vinyl ester resin, which forms a matrix. The rovings are pulled through guides and injected with resin through a die. It is then heated and continued to pull out and cut to length in the factory for whatever length section they're chasing on that particular day. Mechanical property background for the engineers in the room. Composites are, I probably most closely compare composites to timber design. Timber is a fibrous material. It has a lower modulus. Composites have a lower modulus. They're about 1/5 that of steel. So a lot of the designs we undertake are serviceability driven. You need to pay close attention to deflection design and connections. not too dissimilar to timber. As you can see here, FRP produced by Wagner CFT gets a modulus of about 36 GPa, and not all FRP is made equal. So some imported FRP products into Australia can have moduluses I've seen ranging from sort of 10 to 20 GPa, maybe 20, 25 if you're lucky. I haven't seen too many imported that are above that sort of 30 to 40 GPa mark. So it's a really special product. It's very stiff, it's very strong. It performs better than steel and tension, for example. As you can see there, the density of the product is fairly low in comparison to steel and concrete. Down the bottom there, we've just got a couple of cross sections. As I briefly described before, we do bond sections together to create stiffer profiles to span larger distances and carry additional load. So that bonded eye girder on the right-hand side there is predominantly used for girder bridges and sometimes smaller span road bridges. In the past, we've been lucky enough to be involved in some testing programs with Wagners as well. They're not too afraid to jump out in the field and test something. There's nothing better than trying to find out how your structure is going to break, whether it be members or connections. So in the past, we've done testing programs for riveted truss bridges, small scale testing, and also U-girders for the road bridge market. In addition to that, there's been fatigue testing in the background, going up to 2 million cycles for road use in accordance with AS5100. And just behind the scenes there, Wagners again could elaborate on this, but all of their products are tested to ISO and ASTM standards internationally, which is a brief outline of some of those dot points there, but I won't go into too much detail on that. Water sensitive infrastructure is where FRP, I feel, excels. We've done a lot of projects with Wagners in terms of jetties and wharfs and pontoons around Australia and internationally. The product you can set basically in a marine environment for 100-year design life without too much worry. There's viewing platforms, and as most of you probably would have seen, there's boardwalks and bridges scattered around. They're very popular. As I said, you can basically almost put them in the ocean in the spray zone. There's floodwaters and debris actions that can also be accounted for in the product design. In addition to that, water tank columns are another field we sort of approached into a few years ago. Bottom photo there shows some final installation photos of the FRP columns we set up and a load tested column on the right hand side there. So just to get into the ASCE design guide and how that interfaces with Wagner's design guide. So the Wagner's design guide is based on ASCE, which is the American Society of Civil Engineers pre-standard. It's an LRFD manual released in 2010. It is specifically set up around FRP design. So the design guide uses ASCE as a theoretical basis, but there's also a lot of testing that's gone into behind the scenes and appropriately factored to deliver the capacity tables that are at the back of that design guide. The ASCE is a limit state design guide, which is great for Australian engineers. You're dealing with ULS, ultimate limit state, and SLS, serviceability limit state scenarios. And it also deals with creep, fatigue, vibration, and impact resistance, which you can sort of delve into more detail depending on your situation. The two most important things I usually get concerned about when designing with FRP, and especially using the manuals, just making sure you're not doubling up on capacity reduction factors. We'll look at that in the next slide, and just making sure that you as the end designer are appropriately using the adjustment factors for end use. Second to that, and equally as important, is detailing. Just like any structure, if you're designing, it all comes down to the details. So high concentrated loads require anti-crush inserts generally. You can also install some grout, for example, to increase your bearing capacity. Have a think about material interfaces. If you've got FRP sitting on a concrete structure, I'd highly recommend you look at putting some bearing pads in place to separate those two elements. And finally, if you're using I-beam products, such as the BIG product by Wagners, don't clamp the flanges, just keep the connection detailing really simple. So capacity reduction factors. I won't go into too much detail on this. I've just shown it to indicate that behind the scenes, Wagners have taken into account the reduction factors from the ASCE manual. So these are outlined in the CFT guide. but they're essentially built into the capacity tables at the rear of the manual. So if you're going through and doing a design of a joist or a bearer, working out moment capacity, don't go applying your capacity reduction factors on top of whatever number you pull out of those tables that's already there. You'll be doubling up and just hurting yourself. Adjustment factors for end use are the big one. This is entirely the responsibility of the design engineer at the end of the day, and it depends on your structure, where it is located. Is it located in a humidity sensitive environment? Is there an elevated temperature environment you're installing in? And is there sort of chemical additives in that environment that may be an issue into the future? We've also got the time effect factor, which accounts for creep of the material itself. We'll get into that in the next couple of slides, and the deflection amplification factor, which you need to adjust for your SLS serviceability design checks. So time effect factor is generally, if you're doing sort of boardwalks and bridges with light decking on them, it's not usually a governing scenario. Where I usually get concerned with really high knockdown factors on time effect is if you've got say a girder bridge with a suspended slab sitting on a 50-year design life. That's probably one of the first things I pick on. I'd go and make sure that the long-term time effect factors have been applied appropriately, because it may actually end up governing the design of your member over your short-term capacity. There's also short-term time effect factors, but they're much lower. So for example, short-term, you might be in the range of 0.7 to 0.8, maybe even 1 for your time effect factor. Your long-term loads for the 1.35 G is 0.4, so you get a pretty large knockdown in your capacity. I've just tried to pull through. There's an example in the design guide that I've just tried to pull through into this presentation just to keep things simple. So you can go back to the design guide and have a look at these numbers yourself if you want to work through a solution. So going back to the adjustment factors for end use, moisture condition factor. Based on this example we've got in the design guide, it had a relative humidity of 60% for this case. So our CM adjustment factor is 0.85 for strength and 0.9 for modulus. Temperature factor, sustained in-service temperatures in this example was 48 degrees Celsius, and there's the corresponding strength and modulus reduction factors there. Chemical environment was held at 1.0 in this case. It was just in a fairly normal environment. I'd probably get more concerned if you were installing, Wagner's products within a factory environment that's highly acidic. For example, you might have to dig a bit deeper into the chemical environmental factor in that regard. So at the end of this, you've got a adjustment factor for strength and an adjustment factor for the modulus of elasticity, which you need to apply for your ULS design and your SLS design. So those two factors are shown down the bottom here. So for strength, that adjustment factor is 0.64, and for modulus of elasticity, it's 0.75 in this example. So just working through a brief bearer design that is also shown in the design guide. I'm not going to go into detail about how we derive design life, importance levels, or even the load itself. I'm just going to show you indicatively how to utilize, say, the moment you're designing for when comparing that to a capacity of bending moment capacity derived from the manual. So in this instance, we've got a single bearer. It's a 250 by 125 BRS. It's spanning about 1 meter with half a meter overhang either side. This is on a typical boardwalk. The load width is 5.6 meters. We've got a second moment area there. We've got a self weight, and down the bottom, I've just pulled load combination 2 from the design manual, which is your largest short-term load case being 1.2 G plus 1.5 Q. Really simple engineering principles. If you convert that UDL into a bending moment for a simply supported beam, you'll get a moment, design moment of 12.64 kilonewton meters, which is shown at the top here. And what we're doing in this slide is actually just going to the back of the CFT design manual and pulling out your section moment capacity and bending member bending capacities, and just confirming that your knocked down capacity is greater than the design moment. So typical limit state design theory here. So We've got a time effect factor for short-term loading of 0.8 and an adjustment factor for end use of 0.64. So once you apply this to your reduced moment capacity, 0.8 for your lambda, 0.64 for your C, times it by 71.46, which is what we've pulled from the table at the rear of the code for the particular section for its characteristic moment capacity. So once you've adjusted that characteristic capacity with your reduction factors, you end up at, say, 36 kilonewton meters as a overall short-term capacity for your member in bending, and that's greater than the design moment. So that ticks off. The bottom one here is the member design capacity. In this instance, because we've got compression flange restraints at the joist, your effective length is really low. So you're about 1 meter, which is shown in this bottom right-hand table here. We've basically got the same characteristic moment capacity to deal with. Where this changes is if you've got a longer span beam where you don't have discrete restraints in the compression flange, and your lateral torsional buckling will end up governing the design. So that's just something to be aware of, not dissimilar to typical steel design scenarios. Cyclic loading is another important one, not so much in terms of boardwalk application, but definitely important in other structures as well. For this example, I've just made up a scenario where we've got 100 people crossing over the boardwalk every day for 50 years, which gets you roughly for around 2 million cycles over the design life of the structure. We've got a service UDL load from the design manual as well in that example, and converted it to a serviceability design moment of 1.82 kilonewton meters. And we've just used typical engineering principles to convert that to a extreme fibre tension stress of 16.3 MPa. What we're doing now is going to the fatigue check in ASCE guide of clause 2.8. So this formula here, I haven't made that up. That's just directly pulled from the ASCE manual. The C factor, M factor in this equation are both pulled from the same manual. N is the number of cycles, which we have worked out. And we're trying to solve for a stress range to assess fatigue damage or the potential for fatigue damage in this scenario. So once you work that out, the stress range is equal to about 10.5%, and you need to ratio that against your ultimate tensile strength. So this 610 MPa is just pulled from the CFT manual in the member properties section. We've applied an approximate knockdown factor to get 450 MPa. That 450 MPa times your 10.5% as a stress ratio provides a 48 MPa stress limit. So in this instance, you basically tick off and say that cyclic fatigue damage is not going to be an issue for this type of member. This can become quite important in road bridges, for example. So just as a bit of a rundown in terms of typical connection detailing, again, we'll stick on the boardwalk procedure. This is taken from the design manual as well. When we look at boardwalks, we do a top-down approach. We'll design the handrails and then the connection to the joists and the bearers, and look at the decking connection as well. Generally, all the connections on these type of structures are grade 3 on 6 stainless steel. There's riveted brackets, and there's basically bolted connections with inserts. So on the left-hand side here, we've got a typical handrail post to joist and bearer connection. The hatched area represents the anti-crush insert, which goes inside the SHS section to prevent it from crushing under load, and it also increases the shear capacity of that bolted connection itself. The right-hand side is just the side view of that same connection. In particular, if you are designing handrails and the handrail loading is quite high, sometimes we end up looking at stiffening up the rear stainless steel angle plate and bolted connection just to provide a bit more rigidity there. So the decking to the joist connection is fairly standard. It's just a stainless steel screw fixing to the top of the joist. Where this becomes important is if you've got like a high wind load or high flood forces or wave uplift forces on your deck, you'll have to get involved and just make sure you've got the right number of tie down points, basically, as a screw fixing into the joist. The joist is then connected to the bearer with riveted brackets and stainless steel brackets. Finally, probably the main connection on these type of boardwalks is just the connection of the bearer to the pile itself. Again, that hatched line represents the anti-crush insert, and it's bolted with a threaded rod through there and locked off. Pay particular attention, same as any other engineering design. Are you in single shear? Are you in double shear? It's important. Keep an eye on that. If you're designing boardwalk with driven piles, I highly recommend you have a read through the CFT design guide as well. There's a fairly well fleshed out section there on driven pile design. But the most important part in detailing of that connection is ensuring that you've got the anti-crush insert in the base of the pile. Like strongly recommend not going to site and driving a pile into sand or clay without that insert in the bottom. It's a bit of peace of mind. It keeps the section together and creates a bit more structural rigidity for the overall life of your structure. Just to close out, just a few examples of projects we've undertaken in the past and what they sort of end up looking like. So the top picture there is a SM 1600 rated road bridge to AS 5100. Similar to the one on the bottom left-hand side. They're formed with a U-girder system, so made up of SHSs bonded with a flange down the bottom, which is also bonded together and glued and cured. The top flange of that section is just a concrete deck element, so it's a composite section of concrete and FRP, which it works really well. It's a pretty cool design, and we've done fatigue testing on that stuff in the past with great results. The bottom right-hand side is a lesser span bridge. It's a girder bridge with I think it was about a T44 design load on it to the old off-road standards. So it was replacing a timber road bridge program. What most of you have probably seen are the FRP truss bridges around the place. So these are pretty cool, pretty interesting structures. Spans on these are getting upwards north of 40 meters, which is quite significant for FRP materials. The main thing I'd say when you're designing this stuff is obviously look at your ULS design and your connections and your member performance, but also just bear in mind that they are lightweight structures. So you should really have a good look at pedestrian-induced excitation and wind excitation, which is briefly outlined in AS 5100, but you may need to pull into other international standards and guides to try and close out your loop there. They're fairly well received in terms of flood and wave and debris actions as well. Finally, we've done some pedestrian bridges over rail. This particular bridge was designed for Victoria into AS 5100. The real intricate part of this design was just ensuring that it could withstand the concertina train impact load crashing up and impacting on the underside of the bridge. So we undertook a fair bit of finite element modelling, testing as well in the background to just try and get this thing across the line. And that's about all. I think I've harped on enough about connection design, but just it's really important. This photo here is of a project years ago. It looks a bit sick, but it's not a material problem. It's an engineering design and detailing problem. So, it's the same thing. Just ensure you've got enough support bearing in terms of inserts in your section or grouted up your section to ensure that it's got enough carrying capacity, and don't clamp your flanges. Just keep the connection design simple.
Great. Thank you so much, Rohan. Just a reminder, we've got a couple of people who have put some questions into the chat there. If you do have some questions for Rohan, we're just about to go to the Q&A section very shortly. Please pop them into that chat facility at the top, and we will have a look at each and every one of those questions. Just to give Rohan a chance to have a drink of water and have a look at the questions that are in there at the moment so that he can work on a response for those. I'm just going to quickly share my screen and talk a little bit about Wagner's Holdings. So Wagner's Holdings is an ASX listed business. It was established in 1989 in Australia and now has over 1,000 employees over 7 countries, with manufacturing facilities in Australia, the US, UK, and supplies construction materials and services globally. There's 3 main units to Wagner's Holdings. So that's Wagner's Construction Materials and Services Division, which includes cement, fly ash, aggregates, precast concrete, reinforcing including steel and bulk haulage services, Wagner's composite fibre technologies, which we've been talking about designing with today, and Wagner's earth-friendly concrete. Wagner's is still very much a family business, with Joe, John, Neil and Dennis Wagner actively involved in day-to-day operations. All right, so we will go to the Q&A now. Rohan, I think the first question that we have there from Thomas Showman is just asking, is there any research connection capabilities relating to screwing the brackets instead of using rivets?
Yeah, there is. If you do want to use screws instead of rivets, that's okay. If you reach out to the Wagner CFT crew, they will have connection capacities for screws for pull out and shear into 100 and 125 sections, so that there's already been testing done in the background there that you can lean upon.
Okay, great. I might also just jump over here at the moment, and I'm just going to add Dr. Ali Mohammed to the conversation. He is our senior structural engineer, just in case he wants to jump in and add anything as well. So Ali, I've just added you there. Feel free to operate your camera or make yourself visible if you'd like to add anything. We might move on to question number 2 there. I'm just jumping back to my chat. So we've got Michael T. Coots has just asked, are there any materials and bridges TMR compliant?
So the FRP portion isn't directly picked up by TMR, but there are TMR guidelines that have been released, which Ali could probably expand upon a bit further. There's sort of like girder, FRP girder guidelines that TMR have released in the past. Ali, did you have anything additional to add there?
Yes, Rohan. Yeah, basically TMR have released specifications, let's say like for ultruded FRP sections. We're still working with TMR, let's say like on these specifications, but basically we have done the bridges. Basically they are for road tech, which is part of TMR, or basically pedestrian bridges, let's say, following TMR specifications and guidelines. Yeah, so basically we have, let's say, a close relationship with TMR. We have like ongoing research projects with TMR, and yeah, like a few good examples of bridges that already been constructed, let's say, and basically are on the network.
Great, thanks, Ali. We're just going to jump to Willie Bay there. He's asked, is there any guidelines on the edge distance pitch for screw fixings to SHS joists?
There is. I can't remember off the top of my head if we've actually put it in the design guide itself, Ali, but in ASCE, if you get a copy of the pre-standard, they do have a section in there that outlines minimum edge distances for pull-out of screws and bolts.
Great. Ali, we might circle back to Willie and provide him with any details that we have after this webinar as well. Shah has just asked a question here. Do you have, for design application, reference for warehouse type building where we are expecting high wind loads?
Good question. I'm not sure if you're in like going down the path of, say, doing a portal frame out of FRP. We have looked at that sort of stuff in the past. It does depend a lot on the end client and what they want to end up using. In a warehouse application where there's probably been a little bit more success is actually using the FRP as purlins themselves, particularly in acidic environments and internal environments that are a bit more aggressive than normal. And in that regard, you're just designing an FRP structural member acting as a purlin in accordance with the design guide, but using principles from warehouse design for purlin design, for example, out of AS 1170.2, the wind loading code.
All right. We've got Anne has asked the question: will Wagners produce H FRP sections and C FRP sections in the near future? That one might be for you, Ali.
Yep.
There's nothing
Yeah,
like putting you on the spot, is there? If we're not sure of the answer, we can circle back as well.
Yeah, no, definitely I can take this one. Yeah, so basically like the C sections and the H sections, or let's say like any open section, is not part of the manufacturing process at this stage, mainly because of the way we manufacture like the closed sections, because we follow the pull winding technique. Basically, we don't use, let's say, any fiber mats. We mainly use longitudinal rovings, and these rovings are wound around, let's say, like the transverse direction, let's say, to provide the strength in the transverse direction. However, like we have projects where we have, let's say, H sections and C sections, but these C sections are, or let's say any open section, are made of post-processing the existing SHS and RHS sections. In the future, we might get into the space of manufacturing C sections and H sections if there is a need for it. But at this stage, yeah, as I mentioned, it's basically we make the closed sections, SHS and RHS, and any C sections and H sections basically are made of post-processing the existing closed sections.
All right, thank you, Ali. We have got Simon Lewis has just thanked you for your presentation, Rohan, and he's asked the question, when calculating end-use factors, what is considered a sustained condition?
Yeah, it's a good question. Sustained condition isn't really defined in our codes, for example, but if I was, designing I'll use the example of a boardwalk again, you're going to have different end use condition factors if your boardwalk is up in Cairns, up near the tropics, compared to a boardwalk that you might be installing down in Melbourne, for example. You're going to have higher humidity, you're going to have higher, call it sustained temperatures throughout the design life of that structure. So it's not as much about grabbing the absolute maximum temperature and applying it to these end use condition factors. It's probably more about, having a look at BOM data, for example, and just having a look at what the average temperature is over that period of the structure that you're going to be designing for, and just make an informed decision on your end as the designer of what that appropriate knockdown factor might be when you're playing around with those end use factors.
All right. It looks like we've got one last question there. Fabian Risotto has just asked, Ali, we might pitch this one at you as well. If you can elaborate on design considerations for bridges and boardwalks in high fire rated zones.
Yep. Fire questions. It's like we hear this fire question in almost every presentation.
Yeah.
So basically, FRP composite, it is, let's say, a combustible material, but also at the same time like self-extinguished material. So basically, once the source of fire is removed, it will extinguish by itself, and also it takes a fair bit of effort to put it into a flame. For the consideration or what needs to be done, let's say if a specific boardwalk or a bridge need to be constructed, let's say in high or bushfire prone area, basically we can follow the same technique that we are following with the utility poles, which is a recent product that we started manufacturing, and it's been commercially used. So basically we can use a specific coating, intumescent coating that can meet the PAL 40, which is the second highest, let's say, bushfire attack level. And basically, like with that specific type of coating, we can meet like a PAL 40, and we can have structures, let's say, like in bushfire prone areas.
Excellent. Thanks so much for that answer, Ali. And I should just say we've really put Ali on the spot today too. I didn't tell him that we were going to invite him in to ask questions. So thanks very much for being a good sport too. Appreciate that. Simon Lewis has just circled back and just wants to further clarify. How do you determine the capacity of a bolted connection with simultaneous forces perpendicular to parallel to the fibre?
Mm-hmm. Good question again, Simon. The capacities in the back of the design manual are largely along the fibre pull-out capacities, because that's the weakest mode of failure when you're doing connection testing and design. So the values in those tables will be accurate if your load application is along the fibre. If you've got a transverse load application against the fibre, like around the rovings that are on your plus-minus axis, typically we see those actions providing higher capacities for the bolted connection. It won't be quite up to exactly the shear capacity of the bolt, but let's just say it's very close to that. If you're looking at a scenario where you do have those sort of high loads as a vector applied, for transverse and longitudinal in your cross section, I'd recommend reaching out to the likes of Ali or the Wagner CFT team and just having a look to see if you can get a bit more bang for your buck out of using some additional factors in terms of transverse loading and not just relying wholly on the longitudinal, which will be a bit conservative.
Yeah, and at any time, if anybody does have some questions that they want to reach out to the CFT team with, the Wagner CFT team with, just head to our website. On the Contact Us page, there is a file form that you can fill out. Just give us a bit of detail about what you're looking for, and we can absolutely put you in contact with the right person who can answer your question. Last question has come from Juan Pineda. Is there anywhere where we can access standard or typical details?
Yeah, actually in the design guide as well, there's a section at the back which has typical connection details for a boardwalk. If you're looking at something a bit more abstract in terms of truss bridges or road bridges, again, I'd just recommend reaching out to the Wagners team and just requesting. I'm sure they'd be more than happy to send a couple of snippets of what your connection or detail may end up looking like.
Wonderful. Well, thank you very much today, Rohan, for your excellent presentation. It's been very informative, and thank you, Ali, for stepping in there. I'm just going to quickly share my screen here. I wanted to let you know that there is another webinar that's coming up on the 28th of November on how to reduce carbon in construction and meet your 2030 targets. So if you'd like to use your QR code reader now and sign up to that webinar that is coming up on the 28th. If you don't have your QR code reader handy, make sure you sign up to the newsletter, which comes out monthly now, where we will be promoting our upcoming webinars, and you can sign up directly onto those. And for everybody who's attended today, I will send out a webinar feedback form this afternoon, and we'll include details about that reducing carbon in construction webinar on the 28th as well. I think on that note, we will end the webinar now, and we might go out on a couple of these amazing designs that we showcased in the beginning. And thank you very much to everybody who came today, and we look forward to seeing you at the next webinar. Thank you.
Thanks, everyone.
Thanks, Rohan. I'll give you a call if you want to exit now, and I'll give you a call later.
No worries. Thanks,
Thanks
Kelly.
heaps. Bye now.
Bye.